Good morning, guys and girls. Hope everybody's doing well. Gonna try things a little bit different today and see how it goes with the recording and then get this out to you a bit earlier. And then at a normal time slot, see if we want people to just jump on to field questions. So today's theme is I want to talk about properties of solids. So I'll share the PowerPoint with you as soon as I'm done doing this. It will be attached to the same parent square message that has the link to access the YouTube video, where you just watch the stream with the voiceover of this. So, quick recap of what we've done so far. We started out the chapter by talking about properties of liquids. Right? And some of these will be similar to things that you'll see with solids, and some of them will be brand new. So we went through saying about all the things that we wanted to talk about during this chapter. We said what a liquid was, and we said that liquids have these 5 distinct properties about them. They have high densities, and the reason for that was there was not much space in between the particles, which makes them have a lot of mass and not a lot of volume. They're incompressible, same idea, very minimal space in between the particles, so you can't get rid of the empty space to make them compress. Liquids diffuse fairly well. They're close together, but they still have molecular motion. They're able to slide by each other, so the liquids are able to find ways to intermix with each other and eventually disperse one liquid into another like we did with the food dye. Liquids have surface tension. There's a tendency that the particles on the very top of the liquid form particularly strong intermolecular forces with each other. And after yesterday, hopefully you have a much better idea of what I am talking about when I say intermolecular forces or IMFs. They pull the next door neighbor molecule more tightly together, and it creates this tension across the top of the liquid that is greater than what you'll see at the underneath portions of the liquid. This created the bubbling effect when we were looking at the drops on the penny, and it also creates capillary action when we put a liquid in a container made of glass, because you get different attraction forces between the liquid particles and each other compared to the liquid particles and the glass itself. And then last but not least, we said that liquids have the ability to vaporize. That comes in 2 fashions. They can either evaporate, where the surface molecules have enough energy to break the IFs, holding them there and fight through the vapor pressure, holding them down. Or we have boiling, where any particle dispersed throughout the entire liquid has that same ability, but it requires much more temperature. So we walked through all that, and we talked about high density, and all this is review. So we just talked about that. We looked at layering and why the liquids layered the way they did. And we said that had to do with attraction and the idea of polar and non-polar, and they can't be layered right next to each other if you're both polar. And then we talked about incompressibility. And we talked about diffusion. Then we got into surface tension. And then lastly, we got into vaporization, which is going to allow us now to jump into a same sort of description about solids. Right? And if we look at solids and we want to talk about their properties, right, we have to talk about the types of solids. And unlike liquids, there are fundamentally 2 different categories of solid. The first is called a crystalline solid, and the second is called an amorphous solid. And what makes the difference between them is the arrangement of their particles when they form. So what you guys think of as crystals, the things you see at the jewelry store when you buy them, are all examples of crystalline solids. Crystalline solids, when they form in an identical pattern over and over and over again. Right? Which you'll learn is called a crystal lattice. Because the pattern is repeated and it's identical throughout the entire crystal, it gives crystalline solids a particular set of properties. Amorphous solids are still solids, but when they form, they have a very randomized pattern. The particles don't attach the same way throughout. So what I brought up here on the left side for you is a couple pictures of calcium carbonate. And throughout class, I use calcium carbonate as an example. And sometimes I call it marble, and sometimes I call it chalk, and sometimes I call it limestone. And people will say, why is it that the same substance, CaCO3, will have multiple names? Like, isn't it all the same stuff? So it's made up of the same stuff, calcium and carbonate, all right, and calcium atoms, carbon atoms, oxygen atoms. But it's the arrangement that changes the forms that you guys will see. If we look at the arrangement of particles, marble, right, like we see statues made out of, that fancy hallways are made out of, some countertops maybe at your house, right, is a crystalline solid of calcium carbonate. Right? It has a very ordered geometric repeating pattern. So if you look down here, right, you can see you have this same pattern, all right, repeating over and over again, right? This hexagonish like shape, right, that keeps following, right, the same pattern, right? A purple, a brown, two reds, right? A purple, brown, a red, right? Purple, brown, red, purple, brown. So you're seeing a repeated pattern over and over again. And more importantly, the structure is consistent, right? It's the same hexagon stacked over and over and over again. Amorphous solids, on the other hand, like chalk, which is also CaCO3, have a non-uniform pattern. If you look at the one here on the right, notice we aren't seeing that consistency of the hexagon pattern over and over again. You're not seeing the repeated pattern among the individual atoms as we go through. And because of that, their properties will be slightly different from each other. Obviously, I can write on the front board with a piece of chalk. I can't do it with a piece of marble. The marble is much too hard. The chalk is able to be slightly ground up with the pressure I'm pushing on it and make a mark on the board. So their properties will have some similarities, but they'll also have differences. So over here, I started to show you some of the generic similarities and differences between them. Like amorphous solids, like I said, are a irregular pattern of ions, molecules or atoms in a solid. Crystalline or crystals have a repeated regular pattern over and over again. Because crystals have an exact pattern, there is a sharp, which means one distinct melting point, one temperature, and one heat of fusion, one amount of energy needed to make that substance melt. Amorphous solids, like your glasses or your plastics, they don't get one distinct temperature because they have that irregular pattern. So some spots are weaker than others, and the weaker spots will melt first, and the more structured spots that have stronger IFs, they will melt at a higher temp and have a higher heat of fusion. Talking about some examples, glass is a great example of an amorphous solid. A lot of glasstic polymers are amorphous solids as well. Diamond is a great example of a crystalline solid. Most of the substances you've worked with in my lab, the powders, the white powders, the blue powders, the copper sulfates, things like that, those are crystalline, solids. If I took out big chunks of them, you'd be able to see that. Last thing is just a terminology thing. Amorphous solids are referred to as isotropic because they don't have a uniform pattern. Crystalline anisotropic. Right? They do have a uniform pattern. All right, so it doesn't make too much difference in the properties that we're going to talk about, but there will be some. So you should know that there's two fundamental categories of the solids. So if we start getting into these specific properties, some of them are going to sound similar to liquids. For instance, they have shape and they have volume. What might be different is what is measurable about them in their current form. So we've done this for all three of our phases so far. We said that gases over here, they have irregular shape and irregular volume. And the reason is gases expand to fill their container. If I get a bigger container, its volume is bigger. If I get a smaller container, its volume is smaller. So the volume is not a set thing. The gas in a 2-liter bottle is 2 liters. The gas in a 5-liter bottle is 5 liters. Liquids have a definite volume. I can measure them, but their shape is not definite, right? If I take a 2-liter bottle of soda, it is 2 liters and it's the shape of the bottle. But if I dump that bottle into a different container, it will still be exactly 2 liters, its volume, but its shape will conform to whatever the shape of the container is. Right? The forces in the liquid are strong enough to keep them close enough together that they won't escape, but they're not so strong that they can lock them in place. A solid, on the other hand, has very strong forces holding it together. So strong, in fact, right, that the particles can only vibrate next to each other. They cannot separate or slide by each other. So because they can't move, their shape is fixed. If I put a sugar cube in a 2-liter bottle, it's the shape of a sugar cube. It's not the shape of whatever its container is. And if I move it to a 10-liter bottle, it's still the same shape. It's a sugar cube because when I pick up this piece, all of the pieces go with it. So liquids have definite volume but indefinite shape. Solids have both definite volume and definite shape, right? Which is sometimes known as being rigid. A rigid shape means it is unchanging. And like I said, it's because the IMFs, intermolecular forces, are so strong in the solid that the particles are stuck in place, so they are not able to separate from each other. So all solids, amorphous or crystalline, have definite shapes and they have definite volumes. Second property of solids. Solids, as I mentioned, have definite melting points. All right. Now, if you're a crystalline solid, it's one specific temp. If it's an amorphous solid, it could be a range of temps, but the range is still definite, right? It won't vary in range. All right. So crystalline solids have a specific temperature, right, in which the kinetic energy of its molecules overcome the attractive forces holding them together. So melting is all about breaking the intermolecular forces that you see in between particles. All right. So yesterday I showed you, all right, some molecules, and we talked about how we determine whether they have hydrogen bonds or dipole-dipole or London dispersion, right? Or they could be ionic or metallic, and that varies their strength. And when we have enough energy, heat present to overcome those IFs, you will see these molecules start to separate. And that's what melting is. It's the separation of this molecule right here from its next door neighbor. It is not breaking apart this individual molecule, not separating the reds from the grays. That's a chemical reaction. It is separating one gray with 2 reds from a second gray with 2 reds. Right? And the chemical structure controls the strength of the IFs, which is why substances have different melting points. But because the structure is crystalline and it's the same pattern over and over and over again, these IFs are repeated over and over and over and over again. So there's a very specific amount of temperature, which is a reflection of heat, that it takes to shake these guys hard enough that they will break apart. So the solids are vibrating, and as you add heat, they vibrate more, and eventually you get them to vibrate so hard that they have enough energy to break the intermolecular force, holding those two things together. Like I said, for a crystalline solid, though, this isn't one specific number. It's usually a range, and it can spread somewhere in the ballpark, depending on who it is, of 7-8 degrees Celsius. So the amorphous don't have a specific melting point, and sometimes they're called super cooled liquids because they don't arrange perfectly every time. But solids have a definite melting point because they have very specific IMFs that hold them together. Third property of a solid. This is one that is similar to liquids. All right, so I've combined them together. High density, just like liquids, and they're incompressible, just like liquids. Why? For the same exact reason liquids are incompressible. There is very, very little space between the particles in the liquid and the solid because they have strong attraction forces, and the strong IMFs keep the particles packed so tightly we can't get rid of the empty space in between here because there isn't very much to begin with. So liquids and solids are both highly dense and incompressible because of strong intermolecular forces, and there's not much space between them. Similar to liquids, but slightly different. The next characteristic of a solid is that it has a low rate of diffusion. Right? Liquids diffuse, what we would say normal. Gases diffuse very quickly. Solids diffuse next to nothing at all. Now, there are some examples of solids that diffuse into each other, but the process is very, very slow and it's very rare. So we try to focus on the majority of what we're talking about. All right, so solids, because they're so tightly connected, can sit right next to each other, and these red particles here are not strong enough to break away from the other reds, nor are they strong enough to form attraction forces with the blues. The blues won't separate either to let the reds in. Right, so in a liquid, the reds fight their way through the blue, then fight their way through the green, all right, then fight their way back into these reds from either direction. But in a solid, the strength of the IFs is too great that they can't break away and infiltrate the other type of particle. And so molecules from two different solids do not diffuse each other because each solid has attraction forces that are very great. So the strong IMFs keep the particles packed so tightly, there's very little space for the reds to move into, and they can't break away from their own next door neighbor to intermix with the others. So that's going to lead us into a conversation about our types of solids tomorrow. And that's going to let us bring back in the idea of intermolecular forces and how it changes the outcome of the solid category we get. If we have a metallic substance, what does it do? If it's an ionic substance, what does it do? If it's a covalent substance, what does it do? All right, but for today, we're going to leave it at that. I'll attach this PowerPoint, which will include the stuff from tomorrow, into the Parent Square message I'll drop to you guys. Right? And that should help you finish out any questions that you may have had on yesterday's homework, which was the SR 12.1. Make sure that gets my way, hopefully by midnight tonight, please. No new homework today. Looks like it's a very sunny day outside. Get outside, enjoy some fresh air, and I look forward to seeing you guys later on.